What is everything made of? It's one of the oldest questions in human history. From ancient thinkers staring into firelight to modern scientists smashing particles at nearly the speed of light. From the philosophical debates of ancient India and Greece, the search for the true nature of matter has shaped science for over 2500 years. This is the story of atom, its history, its mystery, and how our understanding evolved from myth to quantum mechanics. Around 600 BCE in India, the Vaisheshik school, founded by the philosopher Kanada, proposed that all matter is composed of indivisible, indestructible units called anu. Kanada also believed that atoms could combine in different ways to create various substances, an early insight into the nature of chemical combinations. Around 500 BCE, a Greek philosopher named Democritus proposed a radical idea. Everything is made up of tiny, indivisible particles called atoms, meaning uncuttable. He imagined these particles in constant motion, making up everything around us. But Democritus had no experiments, no math, just thought. Greek science at the time was dominated by Aristotle, who believed in 4 elements: earth, water, air, and fire. Aristotle's ideas won, and Democritus' atomic theory was largely forgotten for over 2000 years. These were philosophical ideas, not testable science, but they introduced the concept of fundamental particles, a notion that would shape science even centuries later. Fast forward to 17th, 18th, and 19th centuries, this time period was the rise of chemistry and scientific method. In 1863, English scientist John Dalton revived atomic theory. He proposed that all matter is made up of tiny indivisible particles called atoms. Atoms of the same elements are identical. Atoms combine in fixed ratios to form compounds. Dalton's theory explained chemical reactions and laws of conservation. Even though we now know that atoms are divisible and can differ in mass, called isotopes, Dalton's model laid the foundation for modern chemistry. Dalton thought atoms were indivisible, but that changed in 1897 by the discovery of subatomic particles. In 1897, J.J. Thomson discovered the electron using cathode ray tubes and proposed the plum pudding model. According to it, atom is a positively charged sphere with a negatively charged electron embedded in it. In 1911, Ernest Rutherford, a student of Thomson, conducted the famous gold foil experiment. He fired alpha particles at a thin gold foil and observed that most alpha particles passed through, but only some got deflected. By his experiment, he discovered that most of the atom is empty space with a dense positively charged nucleus at the center. Rutherford proposed a model where electrons orbit a central nucleus, like planets around the sun. This introduced the concept of atomic nucleus, a cornerstone of modern atomic theory. Later on, James Chadwick in 1932 discovered the neutron, explaining the missing mass in the nucleus. Now the atom had 3 components: proton, neutron, and electrons. Later on, in 1913, Niels Bohr improved Rutherford's model by applying quantum theory. He proposed that electrons orbit in a specific energy levels or cells. Niels Bohr's model of the atom introduced the concept of quantized energy levels and fixed radii for electron orbits. Electrons can jump between levels by absorbing or emitting energy. That explains the atomic spectra. This model worked well for hydrogen or similar single electron species, but struggled with larger atoms. In 1920s, scientists like Heisenberg, Schrödinger, and de Broglie revolutionized atomic theory. Heisenberg introduced the uncertainty principle, according to which we cannot precisely know both position and momentum of an electron. Schrödinger developed the wave equation, replacing fixed orbits with probability clouds or orbitals. De Broglie proposed that electrons behave as both particles and waves. This led to the quantum mechanical model of the atom, according to which electrons occupy orbitals, not orbits. They exist in clouds of probability surrounding a dense nucleus. This is the model we use today in modern physics and chemistry. Deeper insights into the atom came from particle physics. Protons and neutrons are made up of quarks. Electrons are part of a family called leptons. All of this fits into the standard model of particle physics. Today's model of the atom is based on quantum field theory. Particles are excitations in invisible quantum fields. Electrons, protons, neutrons all are not solid balls but energy ripples. The standard model of particle physics describes atom at the deepest level. Quarks make up protons and neutrons. Gluons hold them together, and electrons orbit are based on quantum probabilities. And yet, mysteries remain. What lies beyond the standard model? What is dark matter? What causes mass? And many more. From ancient Indian Anu to quantum fields, our understanding of atoms reflects human curiosity and scientific progress. It's not just about what things are made of, it's about how the universe works at its most fundamental level. Each new model didn't just replace the last, it builds on it, revealing deeper truths. As we continue exploring, who knows, we may yet discover that the atom is just the beginning. Every innovation, from electricity to nuclear energy to quantum computing, is built on our knowledge of the atom. The atom isn't just a building block of matter, it's a symbol of the power of ideas refined over millennia. If you enjoyed this journey through the history of atomic structure, like, subscribe and hit the bell icon for more deep dive science stories, because understanding the atom is just the beginning of understanding everything. Thanks for watching.